the session, your two talks. First one's by Alex Finnegan, and it's titled Modeling Muscle Contraction as a Molecular Ratchet.
All right. Hi, everyone. I'm Alex Finnegan. I've been working this summer with Dr. Steve Desjardins in the chemistry department in Washington and Lee. And our project is modeling muscle contraction as a molecular or stochastic ratchet. So here we go. Quick overview of our talk. First of all, we'll talk about the biological role of the actin myosin proteins in muscle contraction. Then we'll look at what properties of this system make it useful to model as a molecular ratchet. We'll talk about the features of the model that we've produced this summer. Then we'll go on to view some results, their simulated results, and finally we'll talk about the perspective for future work on this project. Okay, so a quick biological overview of the role of actin and myosin. We'll go from the top down. So start off with your skeletal muscles, which are composed of muscle fibers, which produce muscle cells. And within each muscle cell are bundles of myofibrils. And myofibrils are essentially just a series connection of sarcomeres, which are the functional unit of skeletal muscle contraction. And you can see one of the sarcomeres blown up right here. And the way that the sarcomere is put together is you have these red filaments, which are called the thick filament, or the myosin, and the blue filaments, which are called the thin filament, or the actin. And they interact with one another via these red protrusions from the actin filament, or from the myosin filament, maybe, as you can see. So the general idea is that when you want muscles to contract, these myosin heads, or cross bridges, work their way along the actin filament, pulling the two ends of the sarcomere closer together. You can stack up a whole bunch of sarcomeres in a line, and that's muscle contraction. So we have a quick video to watch for YouTube in case my explanation wasn't good enough for you. It's that first part right there, not that. That's kind of the contraction that we're looking at. So, all right. Yes?
Is there a difference between, like, I've heard there's like slow twitch and quick twitch muscles?
There is. And in general, modeling is not at the level where they really distinguish. There's actually a huge number of myosin isoforms, and different isoforms have different properties, and some are slow twitch, some are fast twitch. There's even myosin in transport processes that are involved in muscles. So this is a kind of we're just looking at myosin at a very basic level. All right. Okay, so now we'll go on and look kind of maybe a biochemical scheme of how one of the actin heads would interact, or one of the myosin heads, would interact with the actin filament to produce directed motion. So we start off up top with number one. You have the myosin head bound to the actin filament. That's in the rigor state, which is the low energy state of the system, basically. Then ATP binds to the myosin head and is hydrolyzed. And this hydrolysis, when ATP binds to the myosin head, you get release from the actin filament, and then the energy of the hydrolysis of ATP to ADP and phosphate releases energy that the myosin head is able to translate into directed motion that rotates this domain right here, which is called the lever arm, moving the myosin head to a high energy conformation. Then the myosin head will bind to the next binding site of actin. The release of phosphate triggers the lever arm to swing back to its low energy state, and during the swing, myosin remains bound to the actin, and that pulls the actin to the left there from your perspective. As you can see, by repeating the cycle many times, you can explain the directed motion of the actin filament and muscle contraction. But we're going to take a kind of a statistical mechanics point of view, and we want to recognize that this is not really a deterministic process. Instead, you have the actin and myosin molecules are being bombarded by all sorts of the solutes and the other particles in solution, and we want to take those forces into account. We also would like to recognize the fact that the ADP release and the ATP binding, which are really the slow steps of the process, are also stochastic, and there's actually a low dependency there in terms of the rate at which the myosin head moves from the rigor state to the unbound state and repeats the cycle. And I'll talk about that a little more in just a moment. So given kind of this noise and the stochasticity that the actin myosin system is exposed to, we can also identify some of the different properties of the system that allow it to kind of harness this energy or at least deal with it. First of all, we have the asymmetry of the actin potential, and this is the potential that's experienced by myosin due to the actin filament. The asymmetry will allow the myosin head to harness non-equilibrium fluctuations in the directed motion. We can't harness equilibrium fluctuations because that would violate the second law of thermodynamics. Okay. Also, the myosin head itself is asymmetric, and it has a very specific conformation that with the nucleotide bind pocket here, that's where ATP binds, and then this cleft right here is where the myosin head binds actin. So you can see that it has kind of a very specific conformation, and that is what allows to translate the release of energy via ATP hydrolysis into the directed rotation of the myosin head. So we like to account for that, the ability of the myosin to take that, take the energy and direct it in our model. And finally, there's lots of other mechanisms, and we want to be able to investigate the other mechanisms that are out there, and we proposed via our model, for example, the collective effects of maybe having many different heads working together and stuff. So that's kind of some of those are the properties of the actin myosin system that allow it to deal with the stochastic environment in which it operates. Okay, now I said I'd come back to the slow dependence thing, and that's where we're at now. So again, it's the same biochemical cycle that we showed before. Now we want to imagine the load on the muscle, which would constitute the force opposite the direction in which you want the motion to occur. And if you think about having many of these myosin heads in parallel, if you had a significant load on the sarcomere, you would not want all of them to be cycling, because if they were all cycling, there's a chance you would basically slip and you'd end up with muscle relaxation instead of contraction, which is not what you want. So that's where the rate dependence of the transition from the rigor states into the release comes into play. If you slow down the rate at which you go from rigor to release, you can have more of your actin heads bound, or more of your myosin heads bound, and that reduces the chance of slipping, essentially. Okay, so now this brings us to where we can bring in the ratchet properties of our system and relate it to actin myosin. So first of all, a quick definition. A ratchet is a spatially asymmetric device in which particles can move on average in one direction in the absence of external net forces or gradients. The key word there is can. We need to have a non-equilibrium situation for this to work. If we're in thermal equilibrium, you can't have directed motion of the particles, or that violates the second law of thermodynamics. Richard Feynman wrote a pretty famous lecture on that, and so that's something that we know. So that leads us kind of to define these three essential ingredients for ratchet motion. First of all, we need to have an asymmetric spatial potential that's periodic, and that is what's going to essentially be our ratchet. Second of all, we need the system to be driven out of equilibrium. In this case, we are using ATP to do that, to drive the system out of equilibrium, both through the binding ATP that releases the system, and then also through the energy of hydrolysis that actually causes the myosin head to swing. And then the third kind of a trivial requirement is that all the statistical ensembles of the forces must average to zero, or else you're not really, you don't even need ratchet at that point. Okay, so now kind of the properties in the model we built. The modeling program we're using is called MapleSim. What it does is essentially it lets you specify the interactions, forces, potentials between masses, and also link the masses up, by beams and different joints to kind of constrain their motion. Then the system or the program compiles it all into a big system of differential algebraic equations, simulates it, and hopefully solves it numerically. So I know this looks like a lot, but I figured rather than throwing out a whole bunch of equations, it would be better to kind of visualize how different forces act on each of the different parts of the system. So I don't know how the laser works on this thing. Let's see. Well, where the mouse is, that's represents kind of the thick film. That's the actin, or that's the myosin. And then descending these red kind of cylinders with the masses on the end. These represent the myosin heads. And down here we have the actin filament. Notice that the myosin is essentially fixed, and we're looking for a directed motion of the actin filament. And so that's what we're looking for. We have the potential. This is the potential experienced by myosin due to actin, indicated here. And then we also use green lines to indicate equilibrium points around which each of the myosin heads oscillate. We use the Hooke's law restoring force for this equilibrium position with two different spring constants, because like we mentioned before, there's a preferential direction for the myosin head to swing. K1, which the preferential direction is slightly less than K2. Also, we have a drag force, linear drag force, that acts just on the myosin, not on the actin. And there we can add a load force if we want to do different, for the purposes of experiment, essentially, to try to replicate physiologic data, stuff like that. Okay, now this is just the equation for potential in case you're interested, where W is the measure kind of our asymmetry. Okay, so now that we've talked about kind of the deterministic components of the model, we can talk about the stochastic. Yeah.
Are you looking at a single head, or are you looking at the interaction of the heads working together?
Let me go back here. So each of this potential is the potential that each of these myosin heads experience do their position, and then by the third law we get the third law of motion, Newton's laws of motion, we get the opposite force on the actin. So does that make sense? Okay, so the stochastic effects, we have two of them here. First of all, we have the forces exerted on myosin by the solutes due to collisions within the cellular solution. And we model this as a Gaussian white noise using the fluctuation dissipation relation to give an ensemble average of force to 0, and then the variance is this.